So yes, my presentation actually is not going to be too much about the integration, but will actually be quite specific to the impact of this new printhead technology on the industry as I see it from my position. I've been, well, I have a physics degree from Cambridge, and I've been working in Inkjet for about 20 odd years. In the last 8 years or so, I've been setting up this business, TTP Meteor. And as such, we actually have hands-on experience of just about every commercially available printhead there is. We work in partnership with the different printhead companies, often before the heads become public. What I'm presenting, however, and I'll let you down now, is public information. So I'm not going to present, I haven't got any permission to present secrets from any of the suppliers I'm going to be referring to. So everything I presented is public. You'll see on the last slide, I've actually listed my sources, most of whom are on the internet, so you can check for yourself. Nonetheless, I hope it will be interesting because I've got a viewpoint to give on the information which is out there and the potential for change, evolution, revolution, whatever you want to call it, to the industry that the MEMS manufactured printheads will bring. My company actually creates the electronics for driving these heads. So we're involved in the waveforms and in the power and in the data flow at the head end. We're also involved at the other end, making the data path appropriate for the different industries which these heads go into. So the things which are needed, for example, for finishing, have an impact on how the data is presented to the heads because of perhaps the change in temperature, for example, of your finishing system, making things expand and contract. So you have to change the resolutions of the heads as you go along. That kind of thing. Anyway, so my presentation this morning, I'm going to do a quick summary as to my grasp of what a MEMS printhead actually means, what the implications are for that technology in terms of how the heads are going to perform compared to the heads we've all been used to for a long while, which sort of particular applications might be most impacted by this change. And I think it will be a change. I see this as likely to be the future of inkjet printhead technology in, let's say, a decade or so. There may be most heads made this way. And then lastly, a few things about if these heads do have these particular characteristics, if therefore I'm right about the applications which will most benefit from them, what else do those applications need in order to be able to take the benefit from the new technology? So that's the last one, how to unlock the potential. So very quickly, an explanation of what I think of as a MEMS printhead as compared with a non-MEMS printhead. So MEMS is microelectronic mechanical systems, and what I think of that is sort of silicon MEMS primarily, which in other words it's a structure made by the same industry as would normally create silicon microelectronics. Primarily, the components I'm thinking of are silicon, and then the anisotropic etch methods and the silicon oxide barriers and so on that are used. So in my little diagram here, if this was part of a layer of silicon, very thin, circular disc type thing, and maybe it has a layer in the middle of it of a dioxide perhaps, and you put a mask on the top with a couple of holes in it, and then etch with an anisotropic etch, so in a straight direct line rather than in all directions at equal speeds. It will cut straight downwards through that hole and keep going until it reaches something it can't cut. And then as long as you stop pretty quickly, you won't cut through that layer, but you've got plenty of time to worry about that. So this gives you a machining method that doesn't rely upon a milling machine or some kind of cutter or dicer. It gives you the ability to produce any image you like in photo resist, and then cut down through it to produce a particular shaped hole. Now, the method for doing, I said, is one that's been developed for other technology, for the silicon technology. It does require a fairly expensive fabrication facility to do this, to run this sort of system. And Wikipedia lists 182 fabrication facilities worldwide, which sounds like enough for the inkjet industry, but it's not actually very many, and partly it's because of the cost of these facilities. I mean, $1 billion to build a facility to have the ability to do this. How would you make a printhead out of this technology? Here I'm giving full credit to some guys over at Spectrum now, Fujifilm Dramatics. I contacted them before this talk to let them know I was doing it and asked permission. They produced a nice paper some years ago when they were busy trying to use this on the first Spectra head, the M-class head, which is still available on the internet. So they described how you start off with this wafer, and again with the barrier layer in the middle of it and a photoresist on the top, and you cut your holes into it. Then you do another layer, and you cut again another depth. But this time they stopped it, just using time at an arbitrary depth that they selected. And then they cut in from the bottom, and they did the same on the other side, chopping up. And this time they get through the barrier layer itself. And then by putting and bonding another piece of silicon across the top, they ended up with a closed chamber, which is beginning to look a bit more like the traditional ejection chamber for a printhead. And that we've got a nozzle here, we've got a place for the ink to come in, we've got an area here that might be squeezable. If it is here, see here the piezo put on top to squeeze it down. We've got some sort of barrier here to baffle away the pressure wave as it travels in the wrong direction away from the nozzle. And so we're beginning to recognize this. This is because of one cross-section through one little part of the wafer. As you do different cross-sections, it will look entirely different. Here they're putting the piezo on the top, and here his final diagram shows the path of the ink going through and the drop coming out. So this is the description of how Dymatics were working on developing a MEMS head back 10 years ago. And it's very similar to, I think, to the mechanisms or the methods used for all the different MEMS heads I'm going to talk about today. So designing layer by layer with a photoresist, chopping down, and eventually bonding another wafer on the back to produce your full system. This image here is also in their paper. It shows the baffle region here, but viewed from a different angle. So this is actually an electron micrograph, I think, of the area. So you can see these little baffles are actually columns. And you can see, if you like, the definition, the preciseness of this technology. So there's shapes here which you just couldn't machine. It's too small to make a blade that would cut that kind of shape into a structure. So it's the only way of creating that kind of images like this. You couldn't burn with a laser to get this sort of shape and to get that shape out of it and that repeatability. So this is where the excitement of MEMS came from some 10 years ago in the research departments. People thought we could do something here with an incredibly accurate and repeatable method. And actually, okay, the machine costs $1 billion, but the actual piece part cost is very small because we can make this very, very quickly and make it very, make it very accurately. So here you have the traditional circular wafer, and you can see here someone has shown how, in this pattern, has shown how you might get out of that one wafer an awful lot of these little structures. So each one of these would have, maybe 1,000 or more of these little ejector designs built into one of those. So you can make loads of printheads out of the one silicon wafer. So again, as I mentioned, very expensive silicon fabrication building you need to create this, but actually a very efficient use of time in the sense of very little work involved to assemble this. It's all assembled by that one fab. And you get all those structures perfectly without the tolerancing problems of trying to shoot lasers through Kapton and stuff and worry about how much they burn back and shrink, or whether or not your blade where you're cutting with is getting smaller every time you cut, or if you're using EDM, whether the EDM knife is getting smaller each time you use it, so that there's a change in the size of your nozzles as you go along and so on. So you get a very accurate structure, and you get extremely small structures. And because of this ability to cut down from above, you can have a 2D structure. So a 2D array. You're not coming in from one angle and going through in one direction to do a one line of nozzles or something. You can now do any assembly you want to in 2D, so a 2D drawing, And then with the limitations, as you've seen above, you can actually build up a 3D structure out of it by putting a layer upon a layer or different masks or other masks. So it's not exactly 3D printing, 3D growing, but it's 2D growing in a way that most traditional techniques of dicing, for example, are actually a one-dimensional action. Your blade comes in and travels in one way, you move across, you can do it again, but you can't do multiple steps. Although I say Yoshinori's presentation this morning I thought was quite exciting, the way he showed how they had actually diced in a 2D way with smaller and larger and smaller holes as they created that 2D wafer that they'd done there. So that they have achieved a certain amount of 2D build-up and the ability to get higher resolution in a small area, which I thought was quite a good explanation of how they'd done that with the RC1536 printhead. Anyway, back to MEMS. My summary of the attributes then is that we've got two main attributes. We've got a manufacturing cost that is very low in terms of materials used, but very high in terms of the equipment used, and maybe the yield also if you're not careful. So actually getting a lot of high yield and a lot of volume through your facility makes a massive difference. It's not massively different, to be honest, from many aspects of normal inkjet printhead development, and that often in the old days the lasers were considered expensive, but this is just a factor of 10 beyond that in terms of the cost. And the other aspect is we've got this high native resolution possible, which means if you're aiming to do small drops, you can now do them in a very much smaller area, which means you can do them at a very much lower cost per nozzle. Effectively, the cost per nozzle is irrelevant. It's now a cost per printhead rather than a cost per nozzle, because it's the area of silicon wafer that you need to have no faults in that matters, rather than what the pattern is that you've actually chosen to put in that area. So you're seeing, as a result, 1200 DPI MEMS heads coming out. Anyway, moving on to the commercial side of this and away from my attempts at doing any science to this, the question is who's actually making these and supplying them. There Epson use this technology, Dymatics, Konica Minolta, Rico are the ones I'm going to talk about. There are others, of course, who use it for thermal inkjet. I'm not going to cover those in this presentation. I guess partly because I know very little about those, we don't tend to drive them with the Meteor electronics, whereas we do drive just about every printhead on the market with piezo electronics. With our Meteor electronics, we drive just about every piezo inkjet technology on the market, including pretty much all the ones I'm talking about today. So Epson have been around the longest and do the most. But they are very much restricted to Epson printers and an aftermarket, which is, let's say, less than fully supported by Epson. The Fujifilm Samba, in particular, the Rico, so there was an earlier name class from Fuji. Rico have been using MEMS technologies already inside their heads. I'll cover that in a minute. And Konica Minolta have made some announcements. ZAR are clearly active. You can see it from the recruitment activity. You can see it from the presentation coming on later today. They don't actually make public announcements yet as to the spec of their head, and I'm not going to break any rules on that one either. So there is a variation as to how much you're using. The example I've given so far was of a complete MEMS head. So the MEMS was being used for the entire structure, including the nozzle plates. So the nozzles were part of the structure. Actually, there is a sort of a hybrid option, the Rico GH printhead range, or GH2220 range. It uses a nickel nozzle plate. Sorry, I put it spinning. But the body itself is created out of silicon MEMS. So you get some of the benefit, but not the nozzle aspects of it. Nickel nozzles, I would say, are an interesting thing, and they actually have a proper 3D structure, and they have a curve in 3 dimensions rather than 2. So it may not be a bad idea to use electroform nickel for nozzle plates. It actually gives quite a nice guidance to the ejection. And it has some of the other benefits of silicon in that you're creating a photoresist as a starting point and growing it from that. So it is also fairly inexpensive for the accuracy and high resolution in 2D and so on. Kyocera also, I'm going to mention here, I'm mentioning as a kind of comparison, they produce a 1200 DPI printhead, which again we support. They have done it without using MEMS, and they've done it using lasers and Kapton and, if you like, older technologies. But they've done it with success, or with a great deal of success, in the sense they are the biggest seller, I guess, of 1200 DPI resolution printheads, the biggest seller of 600, probably 600 DPI piezo printheads. So the fact that they're able to maximize or optimize the manufacturing techniques without using silicon MEMS is a credit to them. And I believe they won't fade out for the lack of using MEMS. I believe they've got room to go in driving cost out of their system, if not added performance out of their system. But if their performance is adequate, that's all that matters. Going beyond adequate is always a waste of time and money. So the fact that they have opened the markets already in many areas like textiles and so on with their technology, it goes to show that actually MEMS won't necessarily open a new market, but they might compete. They'll have to compete against a very strong incumbent to get there. So running through the MEMS players here, there's the Epson thin film piezo. Its specs are given. I think you're going to get a copy of the slides later, so I won't read through any specs to you. The issue with the use of the Epson head is that it's great if you're Epson. It's not so great if you're not Epson, because Epson won't support very many partners in the field. Traditionally, they've only had 2 or 3 major partners. They're not really keen on finding more. The fact that the vast number of people in the world do use Epson heads is all because of the ability to get hold of aftermarket heads, which Epson are playing a gamekeeper role trying to prevent happening. So the Epson head price aftermarket wobbles up and down by a factor of 2 to 1. Not particularly a safe place to play if you're looking for stability and you're not one of the preferred partners of Epson. So commercially speaking, this is on the market for Epson, but very few others. The Epson micro thin film piezo technology like this, or printhead, is in use. Here are a couple of examples of Epson printers that use it. So I guess I'm bringing up here to say this is probably the most widely used, the most proven proof that there is, if you like, of the accuracy and ability of MEMS to produce low cost but very high accurate printheads. Now, Fujifilm Damatic Samba. This is a little bit more interesting because it's widely available. Damatics are very keen to find new customers for it. We have driver cards for it available. You can see here there's a Meteor driver cards driving an array. The head itself stacks up in one long line rather than interlaced, in a staggered pattern to get a sort of full coverage. And because of the trapezoidal shape here, it's got all the benefits of the MEMS technology in the sense of highly integrated, very small cross square area, if you like, footprint for a very large number of nozzles, so 2,000 nozzles in a very small amount of footprint. Small drops, they've made very small structures, makes very small drops. Because they're small drops, they can be driven really fast. You haven't got the long wavelength cavities that would make it difficult to run at high frequencies in this. And because it's silicon MEMS, the ink doesn't attack it too much. You've got a full range of inks available, albeit that you've got some very small channels for the ink to work in and not block up. So the ink development is not easy, but it's done. Damatics have been at this for a while. I mentioned the M class historically. Also, this Samba, of course, has been used for a while in the Fuji machines. Here's a JetPress 720. And there have been a few announcements from Damatics over since the last Drooper as to who their partners might be. But apart from this one example of the SPG Prince textile machine there, most of the others that I'm aware of are still in the pre-publicity stage, if you like, of producing their products. But Fuji are very keen to make this product widely available. So in the sense it's been in development for a number of years, it's been proven to some extent by Fuji's own use of it, and now is widely available. It's effectively the MEMS printhead that's available today, with everything to support it, from our drive electronics and software down to inks available and proven with it. I should just reiterate, there's nothing particular, there's nothing private here. You'll find the references to it all on the internet, so you can get the details later. There's no need to take particular photographs of these slides or anything. Now, Konica Minolta have announced a range of printheads. These are not yet available widely. They will be available widely, I'm pretty sure, and that's the announcement. They are working with lead customers. Beyond that, it's difficult to say much. The specs are, however, public, so I've copied them up here for you to see. Given that Konica Minolta has got a very large market presence already for their printheads, comparable, if you like, to Dymatics' market presence, this head, therefore, will be widely available. You know, the sales channels will be there. They will be expecting many customers and be expecting to support many customers. So again, a different relationship from the one from Epson. Commercially speaking, this may not be today, but let's say next year, you should expect to say that there are at least 2 different suppliers of MEMS heads, 100% MEMS heads available. And they've done similar to the Samba head. There are 1,000 nozzles each rather than 2,000, which makes them narrower. And they've done a version which is a 600 dpi. So this, if you like, is the same size in distance, millimeters, as the Samba, and this is the same resolution as the Samba. And being the same, similar technology and similar sizes, we're ending up with fairly comparable sort of throughputs and speeds and range of inks that will be available. The one other difference with the Konica Minolta solution is that this time the heads will not butt next to each other in one color bar. You'll do the traditional 2 rows overlapping. So the pattern on the underside is not of a trapezoidal shape that butts up to its neighbor and overlaps. In this case, you've got the nozzles on the inner side, or the inner dimensions of this, and there's a little distance either side which is not jetting. Hence, you need to overlap them. So when you see these in print bars, you'll see 2 rows per color to get that full coverage. So they're not completely new to this. They have in the past already publicised the MEMS head. I don't make much mention of it here because it's a head specific for a very small market, the printed electronics market. As a drive per nozzle, I don't know if you can see, but that's a very wide cable there with a line basically for each nozzle to allow the electronics driver, in the case it would be someone like Meteor, to actually put a different waveform, different timing to every single nozzle to get that drop consistency that you need for that particular market. So not a low-cost commercial solution. Whereas these heads will be, or these 3 here, these will be targeted commercially to attack the bulk market. I mentioned Rico GX 2020 because it's on the market now. We have driver electronics for it. And it uses MEMS on the inside, but not on the nozzle plate. So the structure, all of the fluid path, has been created by silicon MEMS. So very accurate fluidic path up to the inside of the nozzle plate itself. And that, along with Rico's manufacturing capability to make a great deal of these for the gel printer range, means that, again, the manufacturing costs of this are extremely low for them compared with traditional assembled printheads with many other components within the head, each of which has to be assembled and aligned and done in a particular order to get the alignment best and to hold the tolerances and all that kind of thing. So the older, like 1990s style assembled heads, this challenges those because of that silicon structure on the inside, taking away all of that assembly issues. So there's very little left to actually align between one item and another in the assembly. You've got that efficiency, and you've got that yield benefit, and you've got the accuracy benefit all in coming from the MEMS. But this, say, in contrast to the other ones, although it's it's designed for 600 dpi printing with a 300 npi head, so you have to pass multi-pass over your substrate to get your 600 dpi. Those other MEMS heads were largely targeted at the 1200. Also, Konica will come out with a 600 head, but that will be. And then they have a two-color version of that. So, okay, admittedly, yes, the two-color version will be 300 dpi per color. You could scan it, so it would compete with this area. But this is aimed at the scanning. Okay, I'll have to speed up a little bit after all. Let's move that on. Actual integrators have announced of the GH2220, very few. We've only just been bringing it to market this year, to the general market. The main user, of course, is Rico themselves in a slightly different variant for the gel jet. So it's a very well proven technology, but not actually yet in public domain as the GH2220. More information about it, I've got some data sheets on my booth, and no doubt Rico would have on theirs too. Let's see, I'll have to speed up quite a bit. So what I've said so far, they should be low cost if you get the high volume. They should be very accurate, and they're generally very high resolution. Where would that take it? I'm pressing, yes, here we go. Oh, too far. Okay, I'll have to step in here anyway. So if you want 1200 dpi, I think the most heads in future will be MEMS construction rather than Kyocera's. But the print quality, remember, is not defined just by the accuracy of your silicon nozzle plate. Tons of other stuff comes in. The low-cost aspect of it will mean that people like Epson, Rico, to some extent, maybe even Konica, maybe eventually Samba will be challenging low-cost area. So low-cost printers, DTG, direct-to-garment and signographic type printers will, I think, take MEMS, especially if they're targeted. Now, I believe Rico are going to target them. Konica Minolta may target them. Samba, I believe, is probably more targeted at the single-pass markets. These are less mature, but they're going to grow. So labels, roll-to-roll textiles, commercial print, that kind of thing for Samba. Right. Two things blocking MEMS, perhaps, getting out to the market quickly. One is the inks. Said Samba's been out for a while, so people have been working on inks for that. Rico are working hard on inks for theirs. In some ways, that's less of a challenge because it's a 300 NPI system with a 600 DPI drop, so it's more traditional. So they'll have less problem. Konica, I don't know how far they've got down the ink development route yet with theirs, but maybe the fact that Samba's pathfinded for them will make it easier. The same ink companies will be able to do both. The other area is driver development. We're looking at a lot more data to go through the Meteor electronics than in the past. Not so bad if it's textiles, perhaps, or decor printing because it's the same image over and over. But if it's a commercial print, that's truly quite a challenge to get that amount of data down. But it's needed. I'll skip that one. What else do you need? Oh, yes, of course, these are going into the Samba type machines, 1.5 meter, 1.8 meter wide machines with 160, 240 type heads in it, and an awful lot of data. We have to get we have to avoid the industrial environment electrically. And in the case of Meteor Electronics, we've gone for Ethernet solutions, so gigabit Ethernet to get that isolation. So as I mentioned, yeah, Ethernet, driver cards available that can actually do this thing, actually send this amount of data that fast. There's another problem we're not going to talk about, which is producing the data. That's, as I say, primarily a problem for the VDP, the wide VDP that you would find in commercial print. It's not such a challenge for textiles and decor because you only create the image and then reuse it and reuse it. It's a proven solution as long as the driver cards are around to use it. In the case of what does MEMS do to the challenge for a company like mine, we've got that expandability problem that we're now talking about. Lots and lots of small, physically small heads with a vast number of nozzles in them. And we've been working at 1200 DPI for a few years, so we're kind of used to it. But you still need to be able to expand that. You'll be able to do it with a robust way that all that gigabytes per second of data are not going to get broken by noise on the long cables in an industrial environment. And of course, we've got to try and track that cost, which is being forced out by MEMS. the head price halves, then that's a challenge of my electronics to halve as well in cost to keep track, because otherwise I end up looking expensive. And the low-cost market is a particular new challenge in that if we're going to try and replace or attack the Epson marketplace, then Epson's aftermarket has actually got an awful lot of available Epson components to rebuild a printer out of. And Epson don't like it, and they do their best to stop it. But the people who are using the Epson heads at the moment are basically just re-engineering an Epson printer. And they don't have the skills to actually pick up a challenger printhead to that. So that's a challenge for people like myself to work out how to support those guys when they actually move up into the big bad world of actually only taking a printhead rather than a complete print system, albeit without Epson's knowledge. So that's my summary. I've gone through what I consider the MEMS head to be, what I think we'll be good at, therefore which applications will it attract, and what are the barriers to the speed of entry of the MEMS head in those areas. Here's a list of my sources. So I apologize, it's all public, but I don't create the private data myself, so I can't release it without permission. And thank you very much.